Thank you very much. So I'm Marco Iglesias. I'm a research fellow at Warwick University. I work in the Bayesian inverse problems group led by Andrew Stewart. And what I'm going to present today is joint work with Cody Law from Warwick, Andrew Stewart himself, and myself. So we're interested in data assimilation, Bayesian data assimilation in large-scale inverse problems. And in that sense, data assimilation is an integral part of modeling large-scale problems. And for this talk, I'm going to focus on subsurface modeling applications, in particular in enhanced oil recovery. However, the techniques, the framework that I will discuss today has been also applied to models that are also relevant for weather prediction and can potentially be applied transfer to other disciplines, for example, in climate, in ocean modeling, in atmosphere. One of the common aspects of all these models is that they have uncertain parameters. For example, in subsurface modeling, the properties of the rocks are parameters that have to be specified at every point at every discretization point of the model. So we think of the model for these geophysical applications of a large system of PDEs that we have to solve. We have to discretize, and these parameters are typically highly heterogeneous functions that have to be defined on each of those grids. So we're talking about the size of problems, of these problems of the size of 10 to the 6, 10 to the 8, and that is where the uncertainty comes into the modeling. This uncertainty is propagated through the mathematical modeling model, and it is present in the predictions that we need to use for management and decision making. So we know that even if we characterize this uncertainty, there is going to be propagated through the model, and it's something that we need to quantify. And eventually, we can plug this into an optimal control module. For example, in subsurface modeling, we can use these decisions to optimize controls and increase the profit. So, for example, in other applications, like in atmospheric chemistry, on certain parameters would be, let's say, the initial concentration of a contaminant or the initial state in weather prediction, the initial condition of the PDs. So, as I said before, data assimilation can be thought as an integral part of modeling for these kind of large-scale problems, geophysical problems. But the idea of data assimilation is that we can, whenever we have observational data or data information from whatever we are trying to predict with this model, we can blend data and model into a data assimilation technique to get better parameters. So in that sense, these parameters that then I can plug back here and then get a more accurate model. So in that sense, data assimilation can be thought as an inverse problem where given the output, I want to recover the input. But in the Bayesian framework that I will describe shortly, the idea is that we specify a prior distribution of these uncertain parameters, which can be characterized, for example, for the subsurface modeling application in terms of the geology, properties of reservoirs, and combine observational data from deploying downhole permanent sensors. Both can be combined in the Bayesian framework, and the output of that framework is a probability distribution of these parameters conditioned to that data. So we have what we call the posterior distribution, and that has the goal of reducing the uncertainty that we may have from the prior, given this data, but it also gives a rigorous mathematical formalism to quantify the uncertainty that can be used in this management and decision-making module and then feed back into the control. The problem is that in this rigorous mathematical framework, the characterization of the posterior that comes from this data assimilation in the Bayesian framework, it's for academical problems with the standard techniques, it's very complicated. In real applications, it's impossible. So most of the data assimilation techniques in the Bayesian framework are ad hoc approximations of this posterior. So there is some sort of approximation made in computing the posterior that comes from this data assimilation. So most of the methods that will do data assimilation and quantify uncertainty by means of this posterior will make an approximation, and typically ad hoc approximations that we do not fully understand. So and of course, in order to understand and assess, evaluate these ad hoc methods, we had to be able to fully characterize the posterior distribution, which I just said is pretty much impossible. So one of the lines of research at Warwick in the Bayesian data assimilation group is to develop state-of-the-art Markov chain Monte Carlo methods that allow you to sample and fully characterize this posterior distribution And this is done by defining this in an infinite dimensional framework. I will describe this in the subsequent slides. But once we are able to characterize this posterior distribution, even though it's not practically feasible to do it on real time, that provides us a way to generate a gold standard against to which compare the ad hoc techniques. If we are able to understand by comparing and evaluating these techniques in a rigorous way, we can systematically improve, understand, of course, analyze and improve these ad hoc techniques, which are what you would use here to approximate the posterior in a real-time application. Any questions? Please feel free to interrupt me at any time. So I'm going to start describing the the subsurface inverse problems. The rest of my talk will be basically just to give you an idea of what this Bayesian framework is applied to subsurface modeling. But again, our interest goes beyond the application. However, for a prototypical problem, large-scale problem, we will consider this inverse problem. And the most standard technique, so one of the most standard techniques in haze oil recovery is to inject water in a reservoir fully saturated with oil to recover oil. So let's think in a very simple case where I have a square reservoir. It's very thin, so that there is only flow in the horizontal direction. So I'm looking this from above. I want to inject water in this point, and I'm going to produce oil in these 4 points. So this is a so-called 5-spot configuration. And in order, so the way flow is going to happen depends on the properties of the rock. So what I'm presenting here is a hypothetical plot of the function values of the permeability field. So for example, we see a high permeability here in this area. So this is a hypothetical true. The point is that we don't know it. We can measure at these 5 points maybe this quantity by taking core samples taken to the lab. But we don't know what happened in between. Even in these points, we take cores of the order of centimeters, but the scales here is of the order of kilometers. So there is a lot of uncertainty from these parameters. So what I don't know by you, the unknown, would be the permeability, well actually the log of the permeability. And again, so this depends on the permeability, but of course we need to identify the permeability in the model. So the two-phase flow model that we use is a toy model from the engineering point of view, but it is a quite challenging mathematical problem. The main dependent variables is the water saturation and the pressure. As you can see here, the permeability field, which is exponential of my unknown, appears as a coefficient of the second order elliptic operators. So we have two equations. One equation is linear for the pressure, and the second equation is nonlinear for the saturation. Both of them are coupled here, and these functions are related to the relative permeability of each of the fluid of the reservoir to each of the fluids. So we have water and oil. The right-hand side depends on the well models. I'm not going to the technicality of this. The main aspect is that given this unknown, which is the log of the permeability, we can consider this map that maps you to the solution of the PDE, and then from there we can map into the quantity of interest from the management point of view. So for example, we might think of this to be the amount of oil that we collect at the production wells, or the flow rates, or the bottom hole pressures. But the main point is that it is a quantity that we assume lives in a finite dimensional space. So it typically depends on the number of production wells and injection wells, which for the example that I just showed you is 5. And let's say we have probably 100 times where we collect measurements. So these quantities typically are the order of 1,000, whereas the space where this unknown lives is very high, 10 to the 6, 10 to the 8. So we think of the forward map as a map that maps a functional space into some finite dimensional space. And this forward map has an unknown that we would like to, whose uncertainty we would like to characterize by means of data. So what happens if we knew the truth? So if we knew the truth, then we can evaluate this map, which implies solving the PDE. So I will solve my PDE, and I want to show you the solution of the PDE, which is I'm injecting water here. This is the water saturation profile. Then because I have a high permeability here, then water will come to this production well very fast. And after 5 years of simulation, this is my saturation profile. And then I can compute the quantity of interest, which is my let's say the amount of oil at this production well, so I can quantify the amount of oil given my simulation, and so if I knew the truth, I can give you the right quantity, the perfect estimate. But because I don't know it, what I can measure if I deploy permanent sensors is data from this output. So I can assume that I have measurements at the production wells given by the output of this forward map plus some noise. So I have noisy measurements of what I'm trying to simulate. And the point is, I want to use these measurements to invert these measurements and recover the parameters, or in a statistical framework, give a probability of the parameters conditioned to this data. So the starting point for Bayesian framework is to define an initial prior distribution. And this, for these applications, is typically done by combining geologic information. And the idea is to be able to sample generate possible realizations of this property. So for the sake of this experiment, I consider a Gaussian prior. So I generated different Gaussian random fields that constitute my prior. This is a Gaussian random field. So if you can see the truth looks very close to the prior. And if I want to simulate, now I'm in the case that I don't know the truth, but I know the prior. So you might say, well, why don't you just use the prior and try to see if we can get accurate estimates of that. So this is the truth, but if I don't know the truth and I just try to simulate from the prior, you get completely different answers. Namely, you don't get the breakthrough necessarily at this point. And of course, when you compute, let's say the amount of oil, you get a lot of uncertainty in the estimate. So the truth, the red line corresponds to the truth that I don't know, and these are my estimates. So I see a lot of uncertainty, and if I repeat this experiment, but instead of with 3 simulations of the prior, I simulate 300 times, this is what you get. So you get a very large ensemble. I'm sorry, a very large spread in the uncertainties under the prior distribution. This is something that we typically observe in this kind of geophysical problem. So what we would like to do is to combine my prior distribution with my noisy measurement, which I assume comes from the model plus some noise, which for simplicity we assume is Gaussian. And we can define this negative log likelihood, which is nothing but the weighted misfit of observations minus predictions, which in a deterministic way is what you would try to minimize. In the statistical framework, this allows us to define, in terms of Bayes' rule, the posterior distribution, which is the conditional probability of my unknown given data, and that can be characterized in this way in terms of the Radon-Nikodym derivative of the posterior with respect to the prior. One of the aspects of this, one of the novelty aspects of this research, is that this is done in an inverse infinite dimensional framework. By doing so, we are able to implement the state-of-the-art Markov chain Monte Carlo techniques derived in the infinite dimensional framework that are robust on the grid refinement. So what you would typically see in Markov chains in finite dimensions, that when you increase the dimensions, then you see that all the proposals and you do a random walk are rejected with probability 1 as you increase the size of the problem. These MCMC methods, on the other hand, scale well. So the one that we use, I will just briefly explain, is to generate a sequence of chain starting from the prior. So I take an initial sample from my prior, and then I'm going to generate this Markov chain where at the n step, given n minus 1, I will propose a new function. And the way I propose this function is the following. The difference of the new function with respect to m0, which is the mean of the prior, it's as a weighted combination of the previous one plus some new function from the prior. And of course, beta here is the control parameter between 0 and 1. If beta is 0, then I didn't move. If beta is 1, then I have an independent sampler. Then this proposal ensures all the theoretical properties of the Markov chain. But one interesting point here is that the acceptance probability of this proposal depends only on the likelihood. So if we have a model, not only subsurface flow, but just a way to compute the output of a model, we can easily implement these MCMC for functions and have a very interesting property in terms of being robust under grid refinement. So we apply this MCMC method to fully characterize this posterior distribution of the Bayesian framework and then use it as a gold standard against which compare ad hoc techniques. So I want to remind you how my samples from the prior look, and then I want to show you the samples from the posterior. So if you remember my truth, all they have this, my truth had a low hypermobility area in this region. So you see most of them have similar features, however there is enough variability. If I now, so this is again the truth, so you can appreciate 3 samples from the posterior. Now if I do the simulation as you would expect, I will find some output that is very close to each other, and if I plot the quantity of interest, in this case the amount of oil at each of these production wells, you will see that I reduce the uncertainty. And if I repeat this many times, so before I repeat it many times, I'm going to show you my large spread in the predictions under the prior, and in this case I'm plotting not only the 5 years that I showed you before, but I did a simulation of 5 more years after I did the assimilation. After I put data into the model with my data assimilation technique, this is what happens if I don't do the assimilation, and this is what happens if I do my assimilation with my Markov chain. So I reduce the uncertainty in the parameters, and that is in turn translated or reflected into the model predictions under the posterior. So I'm able to reduce the uncertainty, but the most important thing is that I have a measure of the uncertainty in terms of the posterior, and that is something that you can use in terms of management or catastrophe modeling or something like that. But again, so just a few facts about this. In order to generate this proper full characterization of the posterior, we had to generate 50 million samples. So that was 100 chains of 500,000 each. Took a couple of weeks. This is an academic example. So we cannot expect to apply this in practice. But what we do expect is from this to be able to assess the approximations of the posterior that are typically used in practical applications. So for example, one of the typical approaches to do data assimilation is to minimize this quantity right here, which is the weighted misfit of predictions and observations. So this is actually the log likelihood, and this additional term, which has the mean of the prior. So this term right here actually maximizes the posterior probability, but it's just one estimate, and unless you have a very simple model, like linear, and a prior Gaussian, then this will give you actually the mean of the posterior. In general, what you will see is that this is used as a mean of a Gaussian center at this quantity and a variance defined in this way. And it's defined in this way based on the linearization of the model, because this would be the posterior distribution if this model was Gaussian. I'm sorry, the model was linear and the prior was Gaussian. For these large-scale problems, there's no way this is linear. So what this method does is a Gaussianization of the posterior, and this method, known as 4D bar, is the standard way to assimilate data in weather prediction. There are other more sophisticated, more modern techniques, which, for example, randomizes the noise and randomizes this number, and then you have an ensemble of particles that will give you some characterization of the posterior, and presumably will target multimodal distribution. So in this case, if you just take one estimate and you can be caught in one of the modes, presumably this one will give you many more modes.
You're trying to estimate the covariance, the Gaussian random field, right? That gives you these.
I'm trying to estimate the posterior distribution of the unknown given some data.
Right, but that posterior distribution is a Gaussian distribution, which is.
No, it is certainly not Gaussian. That's what I'm trying to say. Unless this model is linear, which is not the case.
Yeah,
the model is
that's right, but you think you want to approximate it with the
You
Gaussian.
want to approximate, yes.
So you want to, and now you characterize the Gaussian model with a covariance operator.
Yes, exactly.
And that covariance operator you try to estimate.
Yes, by linearization.
Okay, and that takes in your oil recovery problem, that is some sort of function, or what is it? I mean, how do you?
We typically do it with an ensemble. Well, you can you can just plug in this formula and you can generate this matrix.
Yeah, that's right.
So that's very simple.
This is just a finite dimensional object.
Yes. Yeah, well, in terms of the application, but otherwise it's an operator. Right. You can define it as an operator.
Yeah, fine.
And there are also techniques that use ensembles and are sequential, easy to implement. So this is ensemble Cannon filter. So this is another of the typical Gaussian approximations of the posterior. And so some of the work that we've done at work is to assess, evaluate these techniques, and trying to understand more of these aspects. This is, for example, one of those techniques, the one that randomizes the map estimator. This one, the one that randomizes the noise and the mean here. We found that if you look at one of the wells, this is the model predictions under the prior, so this is a very spread distribution. This is under the prior, and this red line, the total red line, is the characterization of the posterior under the model. So you see that it is very narrow because that's where we collected measurements. This green line is one of the approximations. So as you can see, it's quite poor, although this is some of the techniques that people will use to quantify uncertainty. This is another case, this is another example where we have drilled a new well, and in this case the prior, which is this black line, is very close to the posterior, which implies that data that we assimilated was not really informative. So you can compare whether data is informative and you reduce the uncertainty with respect to the prior, or in this case where you actually took measurements and the uncertainty is reduced. So, I said before, even though this was based on subsurface modeling applications, the interest goes beyond that. And so one of the things that we're looking right now is to couple subsurface flow with geomechanics. And so that is relevant in this type of application. So for example, it is well known that land subsidence occurs in highly compactable reservoirs. So for an example of that is in Lake Maracaibo in Venezuela. Subsidence of oil fields have caused floodings. In Mexico City, for example, groundwater withdrawal has caused also subsidence, land subsidence up to 10 meters. So that is a real issue, and doing data assimilation in these couple models and assimilate data not only from flow but also from measurements, from satellite measurements of surface deformation can help to reduce the uncertainty and quantify the uncertainty with this Bayesian framework to assess the environmental impact of applications like this. Certainly in CO2 geological storage is relevant not only the land subsidence, but understanding the coupling between flow and geomechanics is also important to assess the integrity of the cap when you reinject CO2 for geological storage. We are also interested, for example, in applications of overland flow, where we want to assimilate data in this Bayesian framework to estimate or to have a posterior distribution of roughness coefficient. And that is relevant if we want to assess, for example, the risk of some flooding risk. And in that sense, that could be coupled also to some management and decision-making approach where we can use this posterior to design, to optimize urban design in terms of this roughness coefficient. So finally, I would just mention also our recent interest in data simulation for atmospheric chemistry applications, where the aim is to reduce the uncertainty, quantify the uncertainty due to the initial source of a contaminant. That is also important, relevant to assimilate data from the satellites, and the posterior in that case can be used for assessing some type of policy making based on which country emitted what CO2 concentration, things like that. So these are some references, and with that I conclude. Thank you very much.
Okay. Are there any questions? It was a long day. I have some questions, but I'll ask you in the car. Okay. So let's thank the speaker again.